Look at the sheer physical force of fluid dynamics. To engineer an aircraft, we have to map exactly how air separates and flows across the curved surface of a wing. Now, observe a completely different physical reality. This glowing green sine wave represents continuous voltage oscillation, the language of modern hardware and signal processing. And entirely separate from physical hardware, we have software engineering, where artificial intelligence maps complex statistical boundaries to categorize massive datasets. So, what do lifting a jet into the atmosphere, powering a complex circuit, and training an AI classifier actually have in common? If we strip away the metal, the wiring, and the jargon, the physical differences disappear entirely. We are left with a single geometric puzzle, calculating the absolute area trapped between two intersecting lines on a Cartesian plane. These highly complex systems all rely on the definite integral, the mathematical engine for measuring the continuous accumulation of a quantity. This formula computes the precise physical area trapped between an upper and lower boundary. We are going to examine how isolating analytical bounds to calculate this exact trapped space forms the structural logic of almost every major engineering discipline. Because understanding integration means learning the source code of physical and computational reality. Let's look at this Cartesian grid. We have an upward-facing parabola, our function f of x, intersected by an angled linear line, g of x. Our goal is to calculate the exact mathematical space trapped between these two continuous curves. Before any area can be calculated, we have to analytically define where that trapped space begins and ends. Setting f of x equal to g of x pinpoints where the curves cross, giving us our analytical roots, boundaries a and b. With the interval defined, we integrate by subtracting the lower function f of x from the upper function g of x across that span. This specific subtraction sequence mathematically isolates the space trapped between the curves, discarding everything outside our defined interval. It also ensures that any mathematical artifact, like a curve dipping below the axes into negative coordinate space, is safely neutralized in the calculation. The result is an absolute, purely geometric measurement of area, entirely immune to coordinate distortion. Solving for these roots to define a bounded integral is the strict mathematical prerequisite before we can translate abstract geometric space into tangible engineering parameters. Watch as that abstract shape morphs into a physical structure. It forms an asymmetrical airfoil, the precise cross-section of an aircraft wing. Calculating the exact cross-sectional area of this aerodynamic geometry is the necessary first step in wing design. This bounded area dictates the physical volume of the internal structure, which directly determines the total weight of the wing. And those specific volume and weight constraints govern the aircraft's lift-to-drag characteristics when it is placed into a physical wind tunnel. But the application of this math does not stop at the external surface. It applies directly to the internal thermodynamics of the engine. This graph maps a closed-loop pressure-volume thermodynamic curve, representing the continuous phases of a standard combustion cycle. By integrating the exact area trapped inside, engineers calculate total physical work generated. Every component on a massive jet engine test rig is built to optimize the accumulation of pressure and volume modeled by that precise geometric calculation. Whether shaping the airfoil to generate external lift or maximizing internal combustion thrust, aerospace engineering scales entirely on optimizing these integrated boundaries. In electronics, the bounded area represents the physical accumulation of electrical properties. This continuous current time curve tracks an electrical signal as it advances. Integrating this curve yields Q, the total electric charge accumulated over a specific time interval. That specific mathematical sum dictates the physical charge held within hardware components, like these standard cylindrical capacitors on a circuit board. The integral becomes even more vital when calculating the root mean square, or RMS voltage, of complex alternating currents. Finding that precise RMS value relies entirely on taking an oscillating sine wave, squaring it into positive peaks, and evaluating the absolute bounded area underneath. Moving away from physical hardware, we find the exact same principles inside software engineering and machine learning. The waveform transforms into a standard receiver operating characteristic curve, a graph used to evaluate how accurately a classification algorithm processes data. Integrating this bounded area creates a single scalar metric that represents the model's precise ability to distinguish between distinct data classes. Even in computer graphics, rendering engines execute continuous surface integration to calculate how distinct light rays physically bounce and scatter across objects. Whether accumulating electrons in a physical circuit or tracking statistical true positives in code, the underlying geometric process is functionally identical. Modern engineers do not calculate these complex dynamic integrals by hand. They write code to automate the mathematics at scale. To manage the analytical logic, they use Python libraries like SymPy to process pure symbolic algebra. By running this simpy.solve function, the code algebraically locks on to the exact intersection roots, defining our A and B boundaries. Then, simpy.integrate executes the mathematical subtraction established earlier, processing the pure logic within the console. However, humans need numerical visual tools to practically interact with these raw outputs. The matplotlib.pyplot fill-between command instantly shades the trapped area, translating the computed calculus into a clean visual boundary. And working silently beneath all this is NumPy, providing the necessary numerical array structuring that enables these rapid plots to render. We began with pure mathematical roots, translated into aerospace parameters, mapped to electrical storage, and scaled to machine learning. Computationally evaluating and integrating trapped geometric space is the precise structural tool allowing engineers to build the physical and digital world.